All right, good afternoon, everybody. Thanks for joining in. We're going to be having the second part of a talk that we started, I think, way back in April, but because of scheduling issues both on my end and Geronimo's end, we didn't get it scheduled right away. But we are happy to have Geronimo and the AMPAC team here again to talk a little bit more about the work that they've been doing in trying to address microbursts. And for those that were able to see the previous talk, that was sort of more of the theory aspect. And if I'm remembering correctly, I think this one's going to be a little bit more about the practical aspects and some of the work that Geronimo and the team have been able to gather through practice. So I'll throw it over to you, Geronimo, to get us started.
Thank you, Jason. Good afternoon, everyone. Yes, you're exactly correct. So the goal of this talk is exactly to show, like, the first talk. You're seeing my slides and my camera, right?
Yes.
Yes. So the first part of the talk that it was recorded by Jason, it's available through this link, also through the website, the CI Learn to Learn website. But the first part was to talk about, well, what is a microburst, how we detect a microburst, and why it's so complicated, so like almost no one is doing. And then we presented the solution that we built to address this limitation. But there was always that follow-up question is, well, why you're doing all of this? It looks like a lot of effort. So what kind of problem do you see that requires all this infrastructure? So the goal, again, this part is part two, is exactly this. It's why and when detecting microbursts important. And to facilitate this, because this is still like a very kind of personal problem. Like if you have networks that are entirely based on best effort, then I would say the microburst will be more like a luxury monitoring that. But if you have science drivers that require specific resources, or they have a specific time frame, or if they have a very specific flow completion time that you have to support, that's the case for that's the kind of use case that it's important to detect and mitigate microbursts. So to facilitate this presentation, the goal is to talk about one very specific, very famous use case, which is the Vera Rubin Observatory that we're planning to support once it goes production. And then this talk, we're going to talk about the Vera Rubin use case, the microburst a little bit again, lessons learned, conclusions in the future. So again, thank you all for joining. I hope this is interesting. I want to emphasize that it's very good to see this. Like we have 24 people attending this now. It's very nice because this presentation and this effort now, it was very focused on this talk. The idea was to get the best material. It was to get the best way of representing this. It was a lot of effort from the team, and I hope it's helpful. And you let me know if you have any questions at any point. So talking a little bit about microbursts for those who did not see the first talk. Microbursts are just sporadic bursts of traffic that occur in very short time scale. The keyword here is short, very short, because there is no formal definition for that. So it varies when the vendor varies on the authors. Cisco and Facebook, usually when they have publications, they go with the microsecond because they're having solutions for data center. Huawei, Arista, and most of the authors in the literature, they go with the millisecond time scale because it's easy to create tools for that. And mine, as I shared the last time, I also have my own private definition, is any time scale that my network monitoring solution or system cannot detect. If you have an application that runs for 10 seconds, but you only monitor your network every minute, it's still a microburst because you're going to have no visibility. You're not going to be able to properly support that. Obviously, some people call microbursts in this very short time scale because of buffer utilization, but again, this is not a formal definition. Detecting microbursts is a complex activity due to the granularity required to observe those events. And most of the network monitoring solutions, commercial and open source and protocols, such as NetFlow and SNMP, they were not made for that. They were not made for this kind of time scale that we're going to be talking today. And today we're going to be focused on millisecond. It's important to keep like this in mind, that it's not just because it's a microburst and then this could lead to full buffer utilization and packet drops, that's the malicious or is an attack. There are a lot of applications that behave as a microburst, and you still have to accommodate those. So don't think you're mitigating and then you have to just stop all of them. You just have to understand and be supported for that. So this is an example. We're going to be going back to this figure. So this figure is for this presentation. I'm not going to get into the details, but I want you to pay attention to the very small orange vertical line that's pointed by the blue arrow. So you see there's a very tiny up and down. No, it doesn't show like more than 10 gigs, but that in fact is a microburst that lasts 25 milliseconds and it is 100 gig. So due to the size of the chart of the graph here, now the time scale of the graph, and also the size of the microburst compared to how we monitored, you can see that we can barely see it. And the focus of this presentation is going to be exactly to position the microburst in the middle of a flow and see what is the impact. So you can see right away from this figure that the four data transfers on the right side, they are all over the place, right? They go all the way to 40 gigs, all the way to 0. And the first ones on the left side are kind of steady, stable, because the microburst was still not affecting them. But once the orange line gets into the green domain of those data transfers, then you see that it goes all over the place. So this is what we're going to be showing today. So again, this part of part 2, the goal is to answer why and when is detecting microbursts important. And we have 4 research questions. The first one is, how short does a microburst have to be to become a problem? Because it's very hard to simulate, and it's very hard to detect the microbursts. They operate in a microsecond time scale. We don't even have, like AMLite doesn't have a tool for that. We have a tool that the smallest microsecond would be 1 millisecond, but 1 millisecond is 1,000 times larger, bigger than 1 microsecond. And some people define microbursts of microsecond like 80 microseconds or 10 microseconds. So how short do you have to be, or how small the microburst you have to be monitoring? It's important because that goes into a different domain of the kind of resource you have to have. So we want to have like some numbers here today to see, well, yeah, it looks like this size of 500 milliseconds or 5 millisecond domain is enough or not. The second question is, how do TCP congestion control avoidance algorithms react to microbursts? So we're going to be playing most of the time with 2, HTTP, which is pretty standard, and BBR. When doing the data transfers of microbursts the most dangerous? So this is a question that came after once we started analyzing the results, and we saw that it is a very important question. In fact, for me, it's one of the most important ones. We learned that not all the microbursts are the same. And how many TCP retransmissions should I expect depending on the size of the microburst? So again, to help us answer all those questions, we need a use case. This use case will be the Vera Rubin Observatory Network modus operandi. And for those who never heard of Vera Rubin Observatory, we have a good representation today. So KT is here. There's more people here. So if I say anything that is incorrect, please correct me. But pretty much Vera Rubin is a ground-based optical telescope. It's a massive one that's gonna take massive pictures of the southern sky. Right now it's under installation in northern Chile. The estimated time for operation is Q4 2024. And the way how this workflow is gonna work is there is a summit side, which is the picture on the left side, that will be taking pictures of the sky, do some pre-processing of that data, and send the data to the US data facility, USDF, which is based in California at SLAC. And the network that was built to connect those 2 sites, we call long-haul network, is built over infrastructure provided by multiple partners, like Rubin Observatory itself. They had to bury fibers in the desert. Riuna, Rede Clara in Latin America, RMP in Brazil, RedNasp in Brazil, FIU, AMLite in Latin America, Florida Lambda Rail, in Florida, ESNet Internet 2 in the United States, and Slack, which is the data facility. So the picture on the bottom on the right side kind of gives an idea of how many routes we have, who are the sites that are involved in this. And the red line here represents the primary path, which is a dedicated 100 gig circuit, not like an optical circuit, but a dedicated service that goes from Cerro Pachon in northern Chile all the way to Menlo Park, California. The blue lines are the primary backup. The primary backup, or the first backup, is the one that requires some sort of guarantee. So we need to guarantee at least 40 gigabits per second for the blue path. And the green path is best effort. Whatever is available is the last resource. So this is in a simplified view of how this is going to work. So the telescope is going to take a picture of the sky. Last time I heard, the picture was like 6.5 gigabytes. Then there will be metadata that is based on the transient event. There's another 6.2 that will sum up to 12.7 gigabyte data set that has to be moved from Chile to California. And this data set will be generated every 27 seconds. And in this 27 seconds cycle, there is a 7 seconds that is assigned for network data transfers. So that's how much time as network operators we have to carry all the data from northern Chile all the way to California. And this will happen all night long. As long as it's dark and the sky is clean, this is going to be running. The thing is that this data set at the end is still going to be processed again at the data facility, and then it has to be available to the astronomy community in 60 seconds. So that's the reason there's this limitation of a data transfer of only 7 seconds, and that's going to be the goal, right? Even if it's not true anymore, if this changed, but that's what we're going to be using as a use case today. So there is a very high RTT, as you can expect, from Chile to California, and also because of how the network was built based on international and submarine infrastructure. So this traffic goes from Chile to the other side of South America, which is Brazil, then to Florida, and then back to California. So this goes to 120 milliseconds. This graph on the bottom is an actual persona measurement that was built for Vera Rubin. And you can see there, it's a very complex troubleshooting involved here because of this RTT, any packet loss at 10 of power -3 is enough to compromise the 7 second over 220 milliseconds data transfer window. And there's many situations that could lead to packet loss in this case, right? So you can have microbursts, you can have damaged components, transceivers, connectors, dirty fiber, misconnected patch cords. All this can lead to packet loss. So the goal today is to talk about microbursts and how to minimize those. So let's talk a little bit about the experiment, like the methodology we're going to be using here. The response variable or metric is the flow completion time. Flow completion time is the time that it takes for us to send all the data from the source to the destination, right? From the moment that the file leaves one node and gets to the other node, and that's what we call the flow completion time. And that's what we're trying to keep under 7 seconds. So the goal here for this experiment is understanding how microbursts can impact the goal of transferring 13 gigabytes under 7 seconds over a long haul topology. We're going to have 2 nodes, a sender node and a receiving node. We're going to be using Hyper for that, just memory to memory, one stream. We're going to have 2 RTTs for experimentation. We don't have a way of creating an RTT in our topology that is exactly the 220, the 220 milliseconds. So we created 2, one for 209 and one for 301 milliseconds. Basically, the traffic goes from Miami to Sao Paulo, back to Miami in both directions, or Miami to Sao Paulo to Chile, back to Sao Paulo, back to Miami on both directions. Those devices, the sender and the receiver node, they are in the same switch, so there's less than 1 millisecond apart. So we also create a connection for this, for like tuning and creating baselines. And we tested everything before using the RFC 2544, which is like for a bit error rate. And we ran the test for a couple of hours. There was no bit errors. which means that we're not supposed to expect retransmission because of the network, because of errors. If there's any bit error will be, or retransmission will be because of buffer utilization, which is the part that we want to monitor with this experiment. We're going to have 5 to 20 repetitions. We're going to use option -n to simulate the 13 gigabytes of data that iPerf supports. We're using HTTP and BBR, not BBR v2. We don't have this in the nodes, but BBR is kind of similar on the concept, so it's good enough for this. We're going to use a traffic generator to create a 25 gigabits per second microburst that will be sent out of 4 interfaces. So in total, we're going to simulate this in-cast approach where there's multiple incoming traffic and going, everything funneled through one egress port. In total, we'll have 100 gigabit per second of microbursts. Those, we're going to have microbursts of 25 milliseconds, 50 milliseconds, 100 milliseconds, 500, 1,000, and 2,000 milliseconds. And the iPerf traffic that simulates the user data, we'll share this port 2 on the switch with all the microburst flows. And that's where we're going to see the buffer utilization. And everything else about tuning, host configuration, microburst creation, we provide this towards the end of the presentation. There are slides for this. Not planning to go through that. You can download the slides later. But if we have time, then we can go through those details. But that's pretty much standard. A quick disclaimer, a variable in data management, they won't use iPerf. This is just our idea of testing. They will use a different configuration. We are using one source and one destination. They will have 10 nodes sending data, 10 nodes receiving data. So they will have a lot more resources and a lot more buffering and a lot more CPU that we had in our test. They will have different challenges, but I'm just saying that the way how we're doing is not exactly how the data management team will be doing. Okay, this is just for us to test the network. And this talk is just informational. So we don't want to influence anyone to change anything at this point. We just want to show the funny results that we got. So this is the topology. Again, a server on the left side sending data through a Mellanox 100 gig NIC towards another server that is exactly the same configuration. Everything is the same. And then you can see the traffic generator with 4 individual 25 gigabits flow for microbursts coming in the same switch. And then you can see the delays here. We have VLAN 340, 1 millisecond, 342, 209 milliseconds, and VLAN 344, which is 301 milliseconds. All of this is done over the production infrastructure. So all of this is using Memlight. A few baselines before we start so we know what we have. This is the baseline for 1 millisecond RTT. That's not going to be used by anything. It's just like for us to see how much we can generate. And you can see that we have a very powerful CPU because just one flow was one CPU, one core was able to generate a single flow of 65 gigabits per second, an average 59.6. This is obviously the nodes were fully tuned, but this is just iPerf with HTTP. This is the baseline for 209 milliseconds. So you can see that we got peaks of 41 gigabits per second, an average 25 plus gigabits per second for after the TCP slow start. Same HTTP. So you can see here that the average completion time was 6.49 seconds. So this is for 301 milliseconds. We got also good performance, 39 gigabits per second of peaks, 20 plus gigabits on average after the slow start. You can see this here. And the completion time of 9.55, 9.85 seconds for the 13 gigabytes of data. Okay, so now that the methodology, the environment is presented, let's talk about the questions. So we have those 2 questions that we're going to start with. How short does a microburst have to be to become a problem? And how do the TCP congestion control algorithms react to those microbursts? And let's start with HTTP, which is standard. So you can see here in the bottom of this graph, the no microburst, you have three colors here. A blue is minimum, the minimum flow completion time, 6.5 seconds. We have in orange, 6.5 seconds in the median case. And then we have the 95 percentile, which is 7.7. This is no microburst. And then on top of those, you have the vertical line or horizontal lines, microbursts of multiple durations, 2000 milliseconds on top, 1000 milliseconds, then 500 milliseconds, 100 milliseconds, 50 milliseconds, and 25 milliseconds. So this is for 290 milliseconds. And again, this is for HTCP congestion control algorithm. So the findings after the test, those are the tests that we ran 20 times each. So you can see that HTCP has extreme poor performance when you have a microburst. When we don't have a microburst, we manage to stay under the 7 seconds data transfer window that was planned. This is represented by the vertical yellow line here. But any microsecond that any of the microbursts that we tested from 25 milliseconds to 2000 milliseconds, all of them threw everything out of the picture, right? And this became like kind of a concern to see that not the simplest like microburst was addressed by HTCP in time. And the part that got concerned is some of those flows will be are reaching the red line, which represents the next data transfer window, right? So those are separated apart by 22 seconds. Some of those flows are so long that they go into the next data transfer window. And in the worst case scenario of 2000 milliseconds microburst, it went all the way to pass the next data transfer window, because the green line here is supposed to be the end of the next data transfer window. So we can see here that the data transfers vary from, the flow completion time varies from 27 seconds all the way to 37 seconds, which are not ideal. The main concern that this kind of graph shows us is the possibility of a cascade effect, that these data transfer, they start here in the time 0, will be extended toward into the next data transfer window that will impact that data transfer window, and that one will affect the next one and the next one. So this is one of the things we want to do in the future, test again in the future, is it possible that a single 2000 milliseconds microburst happening in one flow affects the rest of the night, or not? It's just going to affect like 2 or 3 data transfers, but then it gets handled later. So this is the kind of concern that I have now after looking those results, because HTCP is the standard approach for the DTNs today. But if you go and start using BBR, still BBR version 1, you can see that the baseline is the same. The flow completion time, 6.5 seconds. We generate the same microbursts, 25 all the way to 2000 milliseconds. And the results are much better, right? So BBR managed to handle microbursts all the way to 100 milliseconds. So the first 4 in the bottom, from the bottom to the top, they were like properly handled by BBR. After 100 milliseconds, we have 500 and 1000. They are not within the 7-second data transfer anymore, but I would say that they are kind of acceptable, right? They are not acceptable if you think of the perspective of an SLA, but they don't go into the next data transfer window. None of them go, even the 2000 millisecond microburst here. So it shows that BBR handles microbursts in a much better way. So those results are much better than if we compare with the HTCP. And the impressive part is that BBR handle all the way to 100 milliseconds with no headache here. It's pretty much like a 200 milliseconds of difference. So when putting those two together on the same graph, green being the BBR and blue being the HTCP, you can clearly see here how they perform when we compare them, right? So again, the yellow line, the vertical line represents the 7-second mark. That's when all of those were supposed to end. And the red one indicates when the next one is supposed to start, right? Which you can see with the HTTP, pretty much any situation that has a microburst affect the next data transfer. So now that we've done this for 209 milliseconds, let's go 301 milliseconds. The chances that it's going to get much worse. And it gets much worse, right? We only added 90 milliseconds of RTT, round trip time, but the average flow completion time increased in 9 seconds, right? So this is borderline the ridiculous number. But so this is if there's no microburst for a single flow with the tuning that we have, HTTP already goes over the 7 seconds, which is represented again by the yellow line. But let's talk about the findings here. You can see that again, pretty much every single microburst forces the flow completion time or the data transfer to go into the next data transfer, which is represented by the red line, right? So again, it shows that HTTP doesn't do well for microbursts, but it's now getting much worse because now we have 3 microburst scenarios that went over the second data transfer, almost getting close to the third data transfer window from this picture here. So again, it shows that HTTP it's not ready for this. And then when we compare with the VBR and under the same circumstances, we can still see that all the way from microbursts 25 milliseconds long to 500, the performance is very similar. We have 10.6 for 25 milliseconds flow completion time and 10.9 seconds for flow completion time for microbursts up to 500 milliseconds. So this shows that for this scenario, BBR is also pretty good. And still, we didn't see a situation where one data transfer goes into the next data transfer window. So there's no cascade effect here. Okay. So again, the same comparison, putting those two together, BBR in blue and HTTP in green, you can see that if you have a microburst up to 2000 milliseconds, which is the one on top of the graph, we can have, instead of 7 seconds, 46 seconds for the flow completion time. And all of this because there was just one microburst that lasts 2 seconds. 2000 milliseconds is 2 seconds, right? So just because we added the 2 seconds of congestion, then the window went from where it was supposed to be 10 to 46. So answering questions 1 and 2, right? So how short does it have to be and who reacts better to microbursts without properly addressing the TCP low start? So this is something that we have to keep in mind always because there's different buffering and we're using iPerf for this. So we're not supposed to expect like performance under 7 seconds for 300 milliseconds. But you can see that neither HTTP nor BBR without microbursts can handle. But that's fine. That's not a problem. That's just part of our environment. But the part that you have to see is that it doesn't matter the size of the microburst as long for those that we use it, right? Any microburst will set HTTP off, and we're not going to be able to close the data transfer, not even close to what the SLA was expecting of 7 seconds. And all of this happens for those who are not understanding why, is because there are packet drops. Because when you have a microburst of 100 gig, and then you have the iPerf traffic sharing the same port, the buffer was going to get full. There will be packets that will be dropped, and those dropped will lead to retransmission. And the retransmission is gonna set the flow completion time to become longer. There will be a picture towards the end that will show this, just one graph for you to see what happened after a microburst. I'm sorry, after a retransmission. VBR proved to be like a lot more tolerant to microbursts, almost 20 times. And for most of the microbursts up to 500 millisecond, it was acceptable flow completion time, acceptable in the sense, again, that it didn't go into the next data transfer window after 22 seconds. It's just not acceptable from the SLA perspective, but it's still acceptable from not creating cascade effect when comparing to HTTP. So any questions at this point? Or should I go to question 3? I don't see anything on the chat. So let's move on.
Yet.
Okay, perfect. So moving on. So this question is new, right? When doing the TCP slow start is a microburst the most impactful? Because those tests that we previously, like I previously showed you, they were just done at the same time. They were like, I decided to do it in the middle of the data transfer. But what if I did this at the beginning of the data transfer or at the end of the data transfer? So let's see this here. iPerf3 usually takes 1 second to start. There's a control, there's a second session just for control to pass all the parameters between the client and the server. After that, usually iPerf takes like 3 to 4 seconds to achieve full bandwidth. That's what you see here at the beginning. You see the timestamps, and you see that at the beginning is 178 megabits per second, 1.6, 16, and then it gets into 28, which is the number we're expecting, right? And then what we're doing is look at this picture on top. The purple part is the same iPerf that you see on the bottom, right? It's exactly the same one. Look at the timestamps to match. What we want to do is create a single microburst of a single duration in each one of these red arrows. So, and the time frame that you see here, right? So we want to create one after the transfer started 1.5 seconds after. Then we want to create for a different TCP transfer after 2 seconds, for a different TCP session 2.5, another one 3.0, 3.5, 4. So each transfer here will only face one microburst, and that microburst will have a different duration, and each duration will take place in one of those arrows that we have here. So the question that I had initially was, if we have a microburst at the beginning, when the slow start is still ramping up, for example, the first 3 arrows on the left side, is this going to be worse? Is going to be the same, or is going to be better if it happens towards the end, right? So this is what we're going to find out now. And this is the result for 209 milliseconds RTT for HTCP, right? So I'll go through the graph again, like more carefully, so make sure that everyone understands. So the y-axis here is seconds for flow completion time. So it goes from 5 seconds all the way to 39, okay? On the x-axis here, we have when the microbursts happen for that flow. If it happened after 1.5 seconds, if it happened after 2 seconds, after 2.5, 3, 3.5, all the way to 7.5. But remember, there was only one microburst of one duration. And the duration is the colors of the lines of the graph. So you can see the legend here. If you have a microburst that's 25 milliseconds is the green line. If you have the gray line, is 50 milliseconds. The most important one is the blue one on top, which is 2000 milliseconds. And then the one under it, which is, I think, is an orange, that is 1000 milliseconds. So if we use the blue one as an example, and the mark of 1.5 seconds, meaning if the microburst happened for 2000 milliseconds, microburst happened after 1.5 seconds, the flow completion time would be almost 39 seconds. But if the same microburst happens at the mark 5 seconds, it would be only 11 seconds, which shows that for HTCP, if you have a microburst at the beginning of the data transfer, at the first 3.5 seconds, then the impact to the flow completion time is much worse. Okay, so again, the higher the number here on the y-axis is flow completion time. Each color represents a different microburst duration. And you can see that for most of the durations, at least 2,000, 1,000, and 500, right away with 1.5 seconds, if they happen at the beginning of that TCP data transfer, that would set the flow completion time off. It will go all the way to 39 seconds, okay? The interesting part is that after the mark of 3.5 seconds, if any microburst happens after 3.5 seconds of the beginning of the flow, the impact is not that bad, right? So you can see that most of the lines after 4 seconds, 4.5, 5, 5.5, they stay under around 11 seconds flow completion time, 13 seconds, or maybe 9 seconds. But what we're seeing here is that anything happening at the beginning is bad, right? Anything happening after 4 seconds, it's okay, it's acceptable. But now let's take a look at the same thing with BBR. So BBR doesn't care if anything starts at the beginning. It's cool, right? So, and once it gets to a certain point, and there's this magic number that we're gonna show later, which in this case here, you can see is 4 seconds. If a microburst happens at the mark of 4 seconds of the beginning of the flow, that's when you are gonna have the worst results. The results here again are the flow completion time being longer, in this case, all the way to 25 seconds, right? So even for small microbursts like 25 milliseconds, you can see at the mark, which is the green line, you can see here that it goes all the way to 18 seconds flow completion time. So when I showed the previous charts, those charts that show BBR doing pretty well, because that was done at the beginning. That was done at 1.5 seconds. That information was in the graph, but I didn't touch on that on purpose. But now you can see that it's misleading, that BBR seems a lot better, but it only depends of when the microbursts happen. It can be as good or as bad, not as bad as HTTP, but can be pretty bad. Because if it happens for 5 and the marks 5 seconds, then HTTP will be doing a lot better, right? So it depends on when the microburst happens, you're gonna have very, very different results. So then I started looking at this, and then I started, let me put all the colors for HTTP the same, blue and red, everything that is BBR. And then you see that there's like kind of a conversion point where they touch that it's around here between 3.5 seconds and 4 seconds, that when they shift profile, like when they shift behavior. And just by accident, I saw that, well, this is 20 times the RTT. When it gets 20 times the RTT, that's when HTTP start becoming better than BBR. So if the microburst again happens after 20 times the RTT, BBR performs worse than HTTP, which it's kind of surprising. I was never expecting to see this, because every time we play with iPerf in the past was just to get as much bandwidth as possible, right? So we keep running for 300 seconds, 100 seconds, 150 seconds. And eventually all of those, if you have the proper tuning, get to the bandwidth you're expecting. But I didn't know that there was these magic numbers here where things would change and change dramatically. Moving on to 301 millisecond, you see that the pattern is pretty much the same, right? You see this for HTTP now, it goes from 1.5 second, all the way to 5.5 second, which is the beginning of the slow start. Remember, this is at 301 millisecond. This is when HTTP performs the worst, right? And after the mark of 6.5, then you can see that the flow completion time goes back to 14 seconds, 16 seconds, or even 10 seconds, right? It gets pretty good depending of the duration of the microburst. But then you do this for BBR, at the same 6 seconds mark is when you start getting weird again, right? So we had this bump here. I don't know what happened here, but we ran this multiple times, right? So it's not just once. There's like 5 or 20 times that this happened, and those are the median values, okay? But you can see here that after 6 seconds, then you have this spike. And the thing that's weird is it doesn't look like it's slowing down after 7.5. So we need a bigger file because 13 gigabytes was not enough. But if this file was 100 gigabytes, maybe BPR would extend with poor performance for a couple of extra seconds that we didn't account here. And then when we then put them together and color everything, and again, the same almost 20 times the RTT is when things start changing in terms of performance, right? So this was an interesting finding to like answering question 3, when doing the TCP slow start and microburst the most impactful. You can see that it changes dramatically depending when that starts. We kind of knew it, right? So we all expect, if you're still negotiating the congestion window and that at that point you have a problem, it's going to be bad. But it's how bad, right? How close to the beginning? And the majority of the tests is every time that you pass the slow start phase. And for example, if you don't have a limitation of 13 gigabytes, you have like a 50 gigabytes. Eventually, when the congestion control window gets to the number, the max number, 1.4 gigabytes, for example, and you have a microburst, it doesn't matter anymore because it recovers so fast that you barely see it. But if it's at the beginning of the TCP session, that's when it becomes like super bad. So for the next figure here, I want to show you the same microburst for the first picture and the buffer utilization. So remember from this picture from the second slide, right? So you can see here, this is the test that we did, right? One data transfer with the microburst a couple seconds before. And you don't see here, but this graph here, it keeps going for another 2 seconds here, okay? So this data transfer, although it looks like pretty steady after 25 gigs, there's like 2 or 3 seconds before that when the slow start was starting. So this microburst here happened during the slow start, okay? And then you can see that little by little, it starts getting closer and closer and closer and closer until the point that it gets to the mark of our 15 hours and 50 seconds. And then you see the behavior is all over the place. It goes from heaven to hell, different from before that it was kind of steady between 18 gigabytes and 30 gigabytes. Now it goes all the way to 40, from 40 to 0, right? And then you can see that something is happening and you can see the burst already inside the flow. And here in the bottom, you can see the same buffer utilization for each one of those moments, right? And then you see you start getting pretty close to 2 megabytes. That's when the random early dropping, detecting dropping methodology for queue management, start dropping some packets, right? So then that's when you have most of the retransmissions. It's when you get too close. It's not when it gets full, it's when it gets close to full. And here you can see 2 flows. The first flow is the baseline, right? No microburst, 7 seconds flow completion time. And then we ran the same one, but created at the 1.5 second mark in 1,000 milliseconds microburst. Look what happened to TCP, right? All of this from the minute 15 second all the way to the right side of the graph. This is the same flow. And look how slow TCP performance increases, right? And when it gets to the end, after 39 seconds, the bandwidth barely got to 16 gigabits per second. And it took it forever. This is the same flow. It was supposed to act exactly the same one as the first one that has no microburst. But because there was a microburst at the early phase, this is an HTCP. We saw that at the beginning is the worst. And look how many retransmissions we had. We only had 12. This is only 12 TCP retransmissions. I know some of you, I said, oh, 12 is a lot. Yes, 12 is a lot. But it's only 12 and it set everything apart. And then you see that the queue was not even fully like full. It was like at the mark of maybe 80% here. So we don't know if there was a packet drop for sure, because this is not something that is easily provided by the hardware, if there was a packet drops, but probably had it because it got to 100 gigabit of utilization. So this is an important observation, because we saw only 12 retransmissions for a data flow that at the end sends more than 2 million packets, but only because 2 failed, then everything else go out to space, right? So this, it's important because it leads to the fourth question. It's like, how many retransmits or retransmissions should I expect depending on the size of the microburst, right? And this will be no chart, it will be just a table to simplify, but those are the numbers from the same experiment that you saw before, right? For the question 3. You can see here that BBR on average has 6 to 10 times more retransmission than HTTP, and it still in some cases performs a lot better, right? But the thing to keep in mind here is that HTTP suffers at the beginning, the mark that goes from 2 to 3.5, and BBR suffers after 4 seconds. But we saw that the worst flow completion time for HTTP was a Mark 2 or Mark 1.5. And look how many retransmissions we had, 15. With 15 retransmission, we perform much worse than when we had 32,000 retransmissions. So you'd say, no, having 32,000 retransmissions is much worse than 12 or 15 retransmissions, but it all depends of when it happened. So the absolute number at the end of transmission of any data transfer that you see the total amount of retransmissions, that number doesn't tell you anything, because if that number was at the end, that's still good. If that number was a fraction that it was at the beginning, that would set everything apart, right? So this it's true here, because you see the number of retransmissions based on those marks. And so in this case, don't assume just because you only saw 2 retransmissions, that's much better than 32,000. It depends a lot of when those 2 happen. And I've seen data transfer during the test that was 1 retransmission at the first packet, and then the TCP session, it took like 10 seconds to recover, just because it was exactly the first one. So this is also a very interesting result. And I'm highlighting in red just the biggest number, but you can process this later. The goal is not to go through individual numbers, but one thing that caught my attention is the number of retransmissions from BBR is like 6 to 10 times more than HTTP. So lessons learned. Well, first of all, TCP is very hard to troubleshoot. We knew that before. We still believe that's real. We are very comfortable with the BPF right now, the extended Berkeley packet filter now. The TCP kernel has a lot of hooks that enable you to see the counters in real time, and applications such as SS is very good for this, for you to see the peak level performance, MSS, retransmissions, pending packets to be acknowledged. You can see all of this, but you don't see why the problem happened. You see the problem happen, but it's hard to understand why there was 1 retransmission in the middle of nowhere. Everything was going fine. There was 1 retransmission. There's no packet drops in the topology. There's no bandwidth bottlenecks, but then why you had just 1 retransmission. One thing that we observe here is that if you have flow completion time in mind, overtuning can be pretty bad. And everyone knows this. This is very famous for data centers. If you have a lot of buffering, your packets will going to be buffered in multiple places, even inside the host. And if you care about this, how fast you complete, the more buffer you add, worse it can get to finish that flow. So one of the things that we had to do is we had to scale down some of the tuning that we did. especially the TCP write memory. That usually we set to two gigs. We had to set to 1 because with the 2 gigs, there was a moment when iPerf is growing its own inside the buffer, and iPerf tried to go over that, and it can and regenerate retransmission, and that kills the flow completion time. When we set the TCP write memory to 1 gig, iPerf never again show retransmissions for no reason. Even I'm saying during the slow phase, even with no microbursts. And we also saw that if you change the initial congestion window, the Linux support, which is 10 times the MSS, if you go there to 10,000 times the MSS, you still have a good performance. But if you go 20,000, then you start going off. So Linux support that, but not necessarily you always go to the max numbers. Well, if you have if you care about flow completion time, microbursts should be addressed. You should monitor those in your network. And in use cases where flow completion time, and I'm saying this because of the Rubin use case here, the best way to address this is to start the slow start before it's time to send it. Even if you send like random data, right? If you send just no like zeros, but you get to the congestion window that you want, and then you place the data to be sent, you're going to perform a lot better, because and your tolerance to microbursts is also going to be a lot better, because once the slow start is done, the protocols are more resilient to microbursts. So in terms of future, we still want to do a lot more tests. BBRV2, obviously, there's new congestion control algorithms based on the INT that we also want to test. UDP quick. We want to understand the possibility of cascade events and find what is the ideal initial congestion window. We want to get closer with the iPerf3 community, because once we now put the iPerf3 results on a microscope that INT created for us, we had so many questions. There's a lot of things that we don't understand is why it's doing that way. So we don't know if it's iPerf, if it's the Linux kernel, but it makes sense to go deeper. And as a strategy now, we have a different perspective how we're going to be addressing this. We're going to create queues for best effort and queues for slow, like a worse than best effort. We're going to change all the flows in our topology eventually to place them in Q1, and Q0 will be for kind of traffic that is very bursty. And our software called BAPM, once it detects it, will redirect those flows to Q0. So I want to acknowledge and thank everyone, everyone that joined the session, but also everyone that participated in those tests. We had Italo, David Miranda, David Ramirez, Renata, Julio, myself, but all those projects, right? So we have people and we have resources from the NSFCC Star Q Factor project, which is going to be our next Lunch and Learn talk. The NSF IRNC MLI-EXP, which supports the network. Vera Rubin Observatory were part and funded as part of the long haul network effort, and Red NASP as well that helps us with that development efforts. So that's what I had in mind. As I said, there is a few slides if you have specific questions about the informant, but let's focus on microbursts. Hey, KT.
And hold on 1 second. Let me allow people to unmute themselves. So go ahead, KT. You can unmute and ask your question.
Thanks. This is a great talk. I noticed that you were injecting the microbursts at the receiver end, I believe, at the destination of the flow. Does it matter if they're coming in at the source or the destination?
That's a great question. So to be honest, Katie, I removed this from this point more test because Italo said that the slides had too much content. It was here. It's like the next test is, does it matter if the burst happened at the beginning of the topology or at the end of the topology? So yes, this is something that I don't know. Just thinking about it, I think it wouldn't make sense because it's the perception of the receiver side. So if he doesn't get the packet, it doesn't matter what the packet was dropped. That's my perspective, but we want to test this. I don't know.
Okay. And then, yeah, we are hoping to use persistent connections and turn off TCP slow start after idle, which will hopefully help with some of these things. So it's like the sending zeros that you were talking about. We'll pay a price at the beginning of the connection, but then if we can maintain the connection, then we can hopefully avoid most of this problem after that. But it'll be good to see how it actually works, and especially with BBR.
Oh, that's great. That's great. So you're planning to keep this all night long, or just for
If we
specific
can,
intervals?
yes. If we
Okay.
can, we keep it up all night.
Okay. Well, that's great. That's great. Thank you for sharing this.
All right, thank you. And thanks for the talk, Geronimo. We have a little bit of time left before the top of the hour here. If anybody else wants to ask a question, you can either type it in or raise your hand or unmute. While we're waiting. Oh, go ahead.
There is a question here that came directly in the chat. Why not BBR v2? No implementation. So the point of BBR v2 is not supported by the kernel, at least the kernel that we had. And those machines are used for another project that we cannot change, George. So we are adding new machines that we can be a little bit more flexible. But the main thing is those machines have a lot of eBPF code that when we switch it from kernel 5.10 to 5.15, the performance got a lot worse. So we decided we're not going to change the kernel towards the end of the project. So the project we're talking about is Q Factor, is the CC Star project that ends in 3 months from now. So I think now is not the time to add new variables. But the goal is to use new machines that we just purchased and receive it to like install a more recent version of kernel and Debian, and then test with BBR v2. It's just because it's not supported by the operational system that we have.
Okay. Looks like Ellie has a question. Go ahead.
Yeah, well, thank you for the talk. I just want to ask, do you think that that magic number that you mentioned with the BBR test, do you think it has to do with when BBR is doing the probing? Like maybe it's just coinciding with when BBR does the probing for the RTT, and then you are injecting the microburst, and that would mess up the dynamics of it? Did you try, like, for example, to see every how many seconds, like if you run these microbursts, when this behavior will happen?
I didn't, and that's a good point. We just like came across this number yesterday, to be honest. That's when this magic number showed up, because we're only testing the first 3 seconds of the data transfer, and this was not happening. And eventually we decided to go a little bit like more all the way to 7, and that's when we start seeing, because we're only concerned about the slow start. And if you see the slow start, it only takes like 3 seconds. So the question is, why is BBR affecting after the slow start is over, right? If it has to be the probing or not. So I would say that it would be very helpful if you could answer or help us guide towards this. But the idea was just to observe and not to go deeper into each one of the findings.
No, yeah, that looks great. And another thing, I don't know if you tried to apply pacing, if it helps with the microbursts, if you have paced traffic, TCP pacing.
For the microbursts or for the
No,
hyper
for the original traffic. For the hyper traffic, not the microburst.
No, we just let it free. Yes.
Gotcha. All right, thank you.
All right, and then I just have one more comment. Since you mentioned that you wanted to work closer with the iPerf3 developers, if you're not in contact with them already, you may want to shoot a note to them, because I know that they're going to be releasing a new version sometime soon, which is going to be almost a completely new rewrite. So that may change some of the behaviors that you've seen.
Oh, well, that's great. That's great. With those tests, we saw that iPerf is not just more reliable in terms of results, but has so many new options that made our lives very, very a lot easier. With the option of timestamp, I would suggest that if we could add timestamp that has milliseconds on it, but that's a C fault because the STRF lib doesn't support it. But there were a lot of new attributes that were very, very helpful. But what I have the feeling is that most of the tests that we have done in the last 20 years, they're always based on, I want to get the maximum bandwidth. I don't have a flow completion time in mind. That was never a requirement. It was just like, I want to get as much as I can. So when we start doing this from the perspective of finishing it, I think there's a few things that iPerf could add that would support us in a different way. So this is what I want to talk to them. I want to understand why it keeps going up and down. This is the main thing. Every 4 measurements, we see that goes down and then goes up. Maybe it's a kernel thing, but yes, this is the strategy now is to start working together with them.
All right. Well, since we're over time, I'll thank you again for the great talk. Send me your slides when you can, and I'll make sure that they get posted. And we will have one more talk next week on another related to TCP topic. It's going to be a couple of people talking about TCP fairness, particularly over high throughput links. So kind of related to this work too.
Yes.
So I hope everybody has a good weekend, and we'll talk to everybody soon.
Thank you all. Thank you, Jason.